who was a joint PhD student of me and Damien Vandenbroek in Paris. Part of what I'm showing was done as started out actually as a master thesis of a former student of mine, Mert Terzi, back in Istanbul. We continued while Mert was doing his PhD thesis in the US. And then my other collaborators are Ido Regev in Israel, Karen Damen at Urbana-Champaign, Tom Witten at the University of Chicago, Eric Clement, Sylvain Patnay, and Damien Vandenbroek in ESPCI in Paris, as well as Shrikant Shastri in JNCASR in Bangalore. Okay, so how much time do I have so that I kind of roughly
1 hour.
Okay, so I hope I won't take that long, but let's start. Okay, and I'm going to start, with a Gedanken experiment. Okay, and so, what you see here is actually this pair of shoes. Okay, and I'm obsessive compulsive. So this was the shoe that I wore for a long time. Okay, and then I like it, so I bought the same brand. Okay, and this is the one before I started to wear it. Okay, and you see, although it's the same make and everything, there are some differences. It's this new shoe, which is actually now this old shoe here. Okay, I needed to break it in. I mean, you buy it and it doesn't feel very comfortable. You have to run and work around until it feels all right. Okay, so the shoe has adapted to your gait, how you walk, what your lifestyle is. So in some sense, your gait, the way you use the shoe, imprints a memory on it. So this is what this shoe looks like after I have used it for a couple of years. Now suppose I have a friend, it's Dor, whom I know, and we have the same shoe size, which you probably don't. So Dor needs these shoes. I said, look, these are wonderful shoes. Here, Joe, I've used them, bring them back. Okay, so Dor takes those shoes, he puts them on, the shoe size is okay, but of course, the shoe doesn't feel right. There's something odd. So he runs around in Amsterdam for a few weeks. It's perfectly fine. He said, great, thanks. Here are your shoes back. And then I take the shoes and I say, wait a moment, there's something wrong with this shoe, right? I mean, so you see, the memory that I imprinted on the shoe got partially erased by Dor, through his lifestyle, and then I had to basically rewrite it on top of it. So this is sort of the theme of this talk. You have a system, in this case, the shoe, interacting with a fluctuating environment, which is me as the bearer, okay? And as a result of these fluctuations, the shoe adapts to your fluctuating environment to be, and that is a process of self-organization. And it is a self-organization process that imprints a memory on this system. And this is what I want to understand. And then I want to sort of, at the end of the talk, I want to ask whether this helps me to understand other systems. So this is an elementary process of history dependence, and this talk will basically bring you through this process. Okay.
Press OK on the button so we can read the title.
Yeah, that is probably a good idea. I was wondering whether I could do something about it. Thank you. It's not my computer, so I don't want to.
Now click on the slides again.
Okay, good. So there is a few reviews, by now classic review in Reviews of Modern Physics from 2019 about memory formation in matter. Shrikant and I wrote a chapter on memory in soft matter in the soft matter roadmap from 2024. Keim and Paulsen wrote a review on memories in the annual review of condensed matter physics, and I, with my collaborators, we wrote this review that is about to come out now, but this is already online, which is basically from where most of the material of this talk is coming from. Good. And so now the shoe is maybe too complicated a system, and we go to a slightly simpler system, which is a disordered or so-called amorphous solid. So, how can you get an amorphous or disordered system, which means you want to prevent it from crystallization? Maybe you can take two kinds of particles that interact with each other on different length scales, and that basically prevents the system from crystallization. We will take a system like this, maybe like a 2D idealized, we are still in the realm of Gedanken experiments, an idealized system, And what we are going to do is we are going to apply a shear deformation, which means we change the shape of the box into a parallelogram. And by the amount, by how much you shape it is what's called the shear strain. It's basically the ratio of this distance to the height of the box. And as I do this, okay, the particles interact with each other. I'm going to do this super, super slowly. So this is going to be quasi-static. And I'm going to do this in a regime where I can ignore thermal fluctuations, which means at any given point in time, the system is in a mechanical equilibrium configuration. Okay, and as I sort of start to deform the box, there is a force of resistance or a stress, and I could sort of measure the stress, the opposing stress that I'm encountering as I'm basically increasing the strain or the deformation of this box, and that stress is basically kind of going up in the zigzag manner, and then eventually it's crossing over into a steady state. The steady state is the onset of yielding with the yield stress around there, which is fluctuating around the value. But on the way to this yielding in the sub-yield regime, you see the response of this box is, the stress is increasing continuously with the strain, but once in a while you have drops in the stress and then it increases again. And what it means is these drops in the stress are mechanical instabilities that develop where a bunch of particles abruptly change their positions, okay? And what's happening is as you shear this, the system tries to move out in this way, and it's trying to move in this way. And at some point, some particles realize, oh, this is not a good position. You should go somewhere else. So some particles are rushing out. So there's a void, temporary void, that is filled by other particles rushing in. As a result of this, you have a long-range redistribution of stresses and displacements of the particles. But there is a localized core, the soft spot, where the rearrangement is happening. And this is maybe not something completely unusual, not unfamiliar to you. You are in a bus. People are coming in the bus. First you move a little bit more inside, but eventually maybe it's getting so crowded that you're searching for gaps out there, holes or open spaces, and you suddenly jump in here. And when you jump in here, you trigger maybe an avalanche. That people are also kind of moving around. That's kind of what you're seeing during such a plastic event. Yes?
This blue line, is it real simulation or real data?
Okay, so this is computer simulation, but this is sort of what you see in real systems. This is actually the technical term is this is a system of 1,000. This data is from a system of 1,024 particles interacting with Lennard-Jones interactions in a 2D deformation geometry.
I guess that also the shape of this curve also really depends on how fast you do your shearing. Or
yes, and as I said, I'm going to be doing it in the most simplest condition of I'm doing this extremely slow so that the response is rate independent. So this is what's called quasi-static, okay? And so the technical term is athermal quasi-static. So I'm doing it sufficiently small so that I don't have to worry about the rates, which means at any given point in time, my system is just in a purely mechanical equilibrium, in this high-dimensional potential energy landscape. But that equilibrium, of course, moves as I drive the system, and this is going to be part of the gist of the story that I will pick up. Athermal quasi-static. We're doing, and the thing is, even that is already quite complicated. So better we understand this before we are out into the universe. Okay. So that's the thing. So I've told you this. So this was now I just increased the shear monotonicity. I see a question there too.
Yeah, what does the yield stress depend on?
It will depend on the preparation of the sample. If this is a very disordered, then the yield stress will just go up and then sort of cross over into a steady state. If you take a sample that is extremely well ordered, you cooled it very slowly, then what might happen actually is it may just shoot up here, and then there's a suddenly catastrophic event, and then it goes. So yeah, and then it flattens out. So a lot of this depends on the sample. I'm going to sweep this all under the rug. Okay, so this was under uniform shearing. Now you could also do this sort of like oscillatory shear. Instead of just going uniformly this way, you go back and then you do this. Okay. Okay, and when you do this, then you find that if the amplitude of the strain is not too large, after a certain number of cycles, the system basically settles into a periodic steady state. So what I'm showing now this time is the potential, the configurational potential energy of the system. Okay, and in the steady state, it is parabolic segments, and again there are drops here, energy drops. So you have again these plastic events here, but this time these events are triggered repeatedly because the system returns to the same microscopic state. And therefore, when you repeat the cycle, it will retrace its effect. So this is now plastic events that are repeatedly triggerable. Okay, so as I said, these are problems whose origin comes from material science. These plastic events can trigger avalanches. This event may trigger some other plastic events in other parts of the system. As you know, one of you guys asked, the response depends on how you prepare the sample, whether it was well annealed, as it's called, or poorly annealed. And typically what had been done is that these plastic events were associated with irreversibility. But as you see, if you cyclically drive the system, then these plastic events, although there's energy dissipation involved in it, okay, they can be repeatedly triggered. The system somehow manages to adjust itself so that a given plastic event can be repeatedly triggered. So it's done, then it's undone, then it's done again, undone. So it's kind of like on, off, on, off, on, off, on, off. Okay? So, and this is sort of behind the idea of memory formation under applied oscillatory shear. So as I said, we've ignored the rate dependence, we've ignored the thermal effects, because even in that limit, the problem is already shows quite complex behavior. So we better understand this before we go anywhere further. Okay? Good. So now, this is a typical way in which you probe for memory in the system. So you apply cyclic shear, what we had seen here, at a given amplitude. So the thing is, you pick an amplitude at which you apply the cyclic shear, and you choose a number of cycles, that you apply this. Okay, maybe until it turns into a periodic state. So once you have this, the result is what we call the trained class. What you do next is, and now again, I'm a theorist, okay, and this is computer, but I can do this also experimentally. But theoretically, I have this configuration of the trained class. I take multiple copies, and for each copy, I apply now an additional cycle of shear, but each copy, I apply the cycle of shear with a different amplitude. So I'm basically scanning a set of amplitudes, that I apply to this trained one. So there's basically two amplitudes. The amplitude with which I prepare the system, the training amplitude, and then a range of what I call readout amplitudes at which I read out basically the response. And again, as a theorist, so I apply a cycle, and at the end of the cycle, my glass is now in a state R. And what I'm going to do is I'm going to ask, how different is T from R at a microscopic level, okay? And how does this difference depend on the amplitude at which I applied the cycle? This readout amplitude, okay? So it's going to be a function. And sort of this is what you get. If you did 0 training cycles, so you didn't do anything at all, this was the fresh glass, and you look at its response, as the readout amplitude gets larger, the distance between the untrained and the readout thing just gets bigger and bigger and bigger, okay? That's maybe not surprising. If you did this experiment with just 2 training cycles, so 1, 2, and now you basically scan, you get the green curve. You see, the distance is low, there's an elbow here, and it goes up. If you repeat it with 4 training cycles, you get the red curve. By the time you get to 10 cycles, you get this curve here. The distances for readout amplitudes up to 6%, okay, which is the amplitude in this case at which you had trained it, remain very close to 0, okay, with a little bit of a peak, and then they shoot up. So this means you can basically read out the memory in the system. There is the cyclic shearing at 6% has changed the system, because initially without the training it behaved like this. It has gone from this to this. It has changed the behavior of the system. It has imprinted some memory on it, which you can read out. Yes?
Does it mean that this only will occur if you have reached a limit cycle?
Well, it will, I mean, yes. I mean, if you don't reach a limit cycle, it might still be, yeah. But it's ideally it will happen when you reach the limit cycle, but if you don't, there's still a trace left.
Yeah, maybe this is more of a semantic description, but memory here,
Mhm.
I mean, you can also just call it, you converge to a more stable state, in the sense that if it's not trained, that you are just somewhere in your phase space. If you train it, you converge to a certain point in your phase space. So
Yes, I mean, this is the correct picture. How you see, I mean, this system can, and we will get it, this is perfect. So maybe hold that thought, because this is where I want to lead to, okay? So your task is to bring this question up again when you think it's the right point to bring it up. So that you have to figure out. Okay, but don't bring it up. Okay, so now this was the theorist. Actually, you can do experiments with a slightly different experimentally, very realizable version of this protocol. And this is like a mixture of polystyrene particles at an interface of oil and water. Okay, and rather, of course, there you cannot have identical copies of the train system, but you have just one train system, and you ring up the amplitude. It's after every cycle you make the readout of amplitude a little bit larger. Okay, so with a single sample, you're scanning a range of amplitudes. Okay, and then when you do this for two different training amplitudes, this is again you see the displacement which you can measure between the trained configuration and the one that you've trained and that you're reading on. These curves basically they stay low and then they suddenly jump to rise just around the amplitude at which you have trained the system. This is so experimentally. This is sort of is observed, and this is coming to Sarah's question. You see, it is as the training amplitude gets larger and larger, it takes much more longer and longer cycles basically to get a periodic response. Moreover, what you find is that the periodic response may span multiple driving cycles. So the system returns to its same state, not after just one peak driving, but after multiple driving. So it's in that case, you see now these response curves for different training amplitudes. And as they become sufficiently large, at the readout matching the training, this doesn't go to zero, but you still see features. You still see features of the training, even at amplitudes where the system is beyond yielding and you're not expecting any periodic response. So, there is a trace of it, and yeah, so there's a trace of this. Good. And so you can now add another twist to this. Well, this is not really the shoe. I've been walking, during the last 10 minutes, I haven't been doing anything periodic on the shoe. Could you repeat the same thing by swapping out the periodic training and do a random cycle? Okay, I mean, what happens there? I mean, it's more realistic. So then, what we do is instead of doing a periodic shear between a maximum and a minimum amplitude, we do a random walk kind of shear with reflecting boundaries at the maximum and minimum amplitude. So you go in fixed train steps. We have a random walk in fixed train steps. Whenever you reach plus or minus epsilon max, the random walk has to reflect. Okay, and then now a cycle is you start at 0, you wait until you hit one of these two boundaries for the first time, then you wait until you hit the other boundary for the first time, and then you wait until you return to 0 for the first time. So these are first passage times, right? And that is basically the first random cycle. The second random cycle then again goes to the first boundary of the previous cycle, so it has to go down first here, then there, and there, and that's the second cycle. And then the readout we will just do by a deterministic cycle. So the protocol will be do 20 random cycles, okay, and then that's your train state, and then you do a deterministic, just simple shear readout, okay. And again, can we capture this epsilon max is the question, and I wouldn't be showing you this if we couldn't. So yes, you can, and so this is for the epsilon max of 0.035. These are these values at which I'm training. These are the distances between the trained and the readout configuration. And you see, they kind of show this, they're going a little bit up, and then they have these kinks, and then they rise very sharply beyond the epsilon max that you're training. Yes?
For the readout, how do you determine the period? Because the random walk doesn't have a fixed period.
Well, it's the period of the driving. Remember, everything is we are in a regime where everything is rate independent. So all I care is how high I go up. I don't care how long it takes to go up. All I care is how high I go up and then how low I go down and then return to 0. Okay? Yes?
If you go to higher number of training cycles, do I expect even the curves for higher amplitudes to converge to something?
The answer is yes and no. I mean, some of these will improve, but there's clearly, we know that there's sort of a critical strain beyond which the system basically yields, you know, and it will be irreversible. So there will be some improvement if you do this for longer cycles, but you know, there is what's called the irreversibility transition you will not be able to avoid unless the system is sufficiently small that it's a finite size effect. Okay, now I'm going to add a little more twist to this, and you see this was a readout with a single cycle. Suppose I add a second cycle to the readout. So now I'm doing 2 cycles of readout. So I've trained it. This is the first, and at the same readout amplitude. So I'm doing a second one, you know, a chaser, if you like, okay? So we've measured the distance between T and R. Now I'm going to measure the distance between the state at the end of the first and the second readout cycle. So between R and R2, okay? What does that look like, okay? And this is what you get here. That's what I call the forward-forward protocol. So this is the distance between the states at the end of the first and the second. And here, you know, it's qualitatively, this is different from here. Let's maybe look at the 0.04, which is this one here, okay? Or this, yeah, it's something, this one here. So it basically mostly stays 0 until the training amplitude, and then it shoots up, okay? So what does this means? That, you know, the distance between R and R2 basically is close to 0 until you reach the training amplitude, and then it goes up. However, in the meantime, the distance between T and R, you see, for the 0.04, you know, increases and goes down, you see? So this means that, you know, the first driving cycle gets you somewhere, right? But the second driving cycle returns you back to where you are. Okay, and this that doesn't depend on, it's independent of where the first cycle got you. You know, the first, if you choose a different readout, it gets you here, but the second, again, returns you here. Okay, and this happens as long as the readout amplitude remains essentially below the training amplitude, and then it starts to rise up. So this means, again, so this shows that there is a reversibility. You know, I mean, I have no control where the first readout amplitude gets you, as long as you're not matching the trained amplitude. But the second is kind of guaranteed to get you back to where you got, as long as the readout amplitude doesn't exceed what you had trained into. Okay, so again, we've imprinted some number into the system, which we can probe. And so there's up to that number, there is some emergent mechanic reversibility because I came to return to wherever I got, and it doesn't matter where I had gotten to, okay? It's, I mean, you know, depending on the different readouts, you get into different places, but you return to those places. So there's, you know, but this holds only up to a certain point, okay? And now maybe if you're familiar with magnets and ferromagnets, okay? In ferromagnets, you would expect this curve to be flat, irrespective of whether you trained the system or not, you know, because, okay, so in that sense, this is sort of like a pseudo-ferromagnet that behaves ferromagnetic only for as long, to the extent that you have trained it, okay? But this is maybe as an aside. So with that now, okay, so we've basically talked about self-organization and plastic reversibility, and it is emergent. Maybe this is pretty apt probably for this institute. You know, it is a property that was not in the system, but that has emerged in the system by basically doing this, you know, random or cyclic deformation. It is emergent. And it is, I mean, you know, and it is basically your deformation has encoded some information into the system. It has encoded it into its microstructure or its disorder, okay? And we can probe this by various readout protocols. So I want to understand this. I want to see how generic this is. And, you know, the key ingredients are probably the disorder, frustration, meaning that as something becomes unstable, some other pieces in the sample can become stable, or they can become unstable. That's the, okay. And of course, I have a large number of degrees of freedom. As I said, the phenomena are already complex enough under atrial quasi-static driving, so I will just stick to this. The other thing that you notice is that although I have a system with a large number of degrees of freedom, the configurations of the particles, I'm applying a one-parameter deformation. Okay, and I'm doing this under athermal and quasi-static conditions. So in some sense, I'm driving a high-dimensional system in a very low-dimensional manner. Okay, and this is going to be now key. because this allows me to describe the system in terms of transition graphs. So, okay, what's the idea? Let me abstract this. So this is, as I said, it's a system with a huge number of configurational degrees of freedom. And I'm going to plot this as a one-dimensional axis here, okay? This is sort of the axis of the high-dimensional configurational degree speed. And on this axis, I have my one-dimensional, honest-to-goodness, one-dimensional deformation parameter, the applied strain. We are under athermal quasi-static conditions. So at a given strain, the system is in some particle configuration that is locally stable. Okay, which I will, this will be the configuration X at some strain X, epsilon. Now, as I start to apply in a slowly adiabatic manner my strain, as we said, the configurations will deform. So this means that my configuration point will move in the configuration space along a one-dimensional hypercurve. And this will continue until an instability forms, okay, where the potential energy is basically is not positive, the Hessian of the potential energy is not positive definite anymore. The first time a zero eigenvalue appears, okay? As long as I don't exceed that point, I can go back along the same curve, return to my point configuration X, and then go in the other direction, and then again, an unstable mode will appear, okay? And so along this thing, I can go forward and backward, and everything basically responds continuously. This is actually the implicit function theory, applied to this thing, if you want to think about it mathematically. Now, at this point, I'm triggering a plastic event, an instability that gives rise to something. So, and I will basically, the configuration at constant strain will jump to some new configuration, which is now stable, and that will sit on its own branch, okay? We will call these mesostates. And so I can abstract this picture into, all of this here, this little kind of spaghetti here is really boring, elastic. So this will be a single state, which I will call A. And this single state has two instabilities, namely when the strain is too large in the forward direction or it's too large in the negative direction. So, and at those points, I'm basically jumping to another spaghetti, which I call B or C. And my convention will be, the red or orange will be if I do the jump from the lower threshold, and black or gray will be if I do the jump from the upper threshold. Okay, so each of these spaghettis has exactly two limits. I've collapsed the spaghetti, the string, if you like. This is my solid state physicist string. I've collapsed the string into a single point, and out of the string, I have basically two exits. Okay, of course, so these lead to these, and of course, these strings also have two exits. So these are here. And now I could basically just follow the transitions and see what I get. And in fact, I can do this with molecular dynamics simulations. So I return to my system with 1024 particles, and and I can basically get a transition graph. It's a directed transition graph. Every vertex basically has two exits, okay, and they are marked an upper and lower exit, which I color code, and this is what you get. So this is, I started my glass here, and it has two transitions. The triangles basically mean I don't know where you go from there. Okay? Now I can execute the two transitions from these triangles. This was generation 1. I'm ending in generation 2. You see, from this triangle, the lower transition leads to here, the upper goes to here. From this one, the upper transition leads to the same state, and this one goes somewhere else. Now I can do this in the next generation,
How do you define states? Because the position of these is continuous.
Yes, but you see, it is. So how could I distinguish this from this one, right?
Yes.
Okay, so first of all, the simplest thing is, if these are equal, they should have the same ranges of stability, right? Otherwise, it's already game over. Yeah. This is a necessary, not sufficient condition. Necessary, if this spaghetti is the same spaghetti, right? They better have the same ranges of stability. Okay, so suppose, okay, so if they have the same range of stability, then they have a common strain at which both of them are stable, right? So at that strain, shear the system to that strain. Now you have two configurations at the same strain, just compare them. If they are identical, the system is completely deterministic, right? Then their future response is the same. So it can be done. let me leave it there, okay? It's a technical question. It can be done. There's no problem with that. Okay, okay, but the point is, although, at every point we have two options, right? There are certain choices that bring us back to the same states. So let me sort of click through this. So this is what it looks in generation 10, and I fast forward to generation 25, and this is where you are. This is the graph. And sort of, first of all, I've placed the vertices so that they're kind of arbitrarily placed, but so that they don't basically, the transitions don't crisscross too much, right? And you see structure in the graph. There are tree-like regions, there is sort of, there are bottlenecks, in order to get from this to here, there's only a few states that you're transferring to, what's called high in-betweenness centrality, in this graph. And so, but the other thing, so the complex dynamics, basically, of the system, the complexity has been now moved into the graph topology. The other thing that you see is that, this is basically, I started from here, I went up to 25 generations, which means this is every set of states that you can reach by going through up-down instabilities, sequences, strings of up-down instabilities of length 25. So if each of these, as you were saying, was leading to a completely different state, this would be a binary tree of depth 25, which has 2 to the 26 states. 2 to the 26 turns out to be 60 million. Okay, what you see here is 1,400 states. It's like a factor of 1,000 lower, which means that a lot of these up-down sequences lead to the same state. So this is a first sign of showing, where this mechanical reversibility is coming from. There's a degeneracy of different binary sequences that lead to the same state when applied to the common initial state.
Yes, we'll map this graph experimentally also. Is it based on simulations, hopefully there.
No, this is I don't.
You can
you can try, but it's not easy. You can try, but it's not easy. And maybe I should. So you can design. Okay, the answer that you want is it's hard. But I think what I want to say is, this is a way of thinking about the system, which allows you to sort of, it's something that I would call is a metaphoric model, which maybe it's not experimentally realizable, but it points towards non-trivial things, that might be applicable for a large, it allows you to look at experimental systems. It gives you a gestalt or some Gedanken thing in the background with which you can revisit. What would it look like if I did this on the, I think the purpose of this is providing conceptual tools of getting a handle on this evolving disorder, on this system.
But can you get any property out of this graph?
Yeah.
You could then test.
Yeah, I think so.
Without having to do all the transitions.
Yes, first of all, okay, so first of all, I started with a system of continuous degrees of freedom, right? And I basically, what I get at the end, the continuous part was basically the elastic part. I basically modeled it out, right? And I ended up with a discrete combinatorial object, okay, which is, it's a random graph. Why is it random? Because the initial condition comes out of an ensemble. Once I have this initial condition, everything else is a deterministic process. It's kind of like the random seed of a random number generator, okay? You choose a seed and the random sequence is determined. Here you choose a seed and you get a random graph, okay? So understanding the topological properties of this graph is a lot easier than looking at sort of a system with 1,000 degrees of freedom. And that's what is behind the reversibility. So yes, we will get to, so bear with me. So there's certain things, I can start to model this with theoretically, it's a discrete object. It's I have choices going to the left to right. It has a flavor of a branching process, I would like to out of this graph, I would extract this is sort of the next step. I would like to extract some parameters, transport coefficients, if you like, that basically will characterize a set of classes, and that I would like to relate to the physics of how I prepared this, and how this. That's the program, okay, and that's where with my collaborator we are kind of going towards. Yes, you choose.
So, in response to a previous question, you said that asking whether two states are the same one or not is technical.
Yeah.
But what happens if your system is marginally stable and I expect minima to potentially be nested one within the other and be very, very close to each other? Both in terms of detection and in terms of the structure of this graph, I guess.
I mean, these are all in some sense limits of driving things to its extreme, maybe making the system larger, as I said, I mean, I think part of these questions can be addressed, but let's start with the simplest one. I mean, let's start that the system is sufficiently large so that it does complex things, but not large enough that I have to sort of ask about limits, in the large limit, every time I do something, something happens somewhere in the sample, okay? So the large n limit is non-trivial, but the large n limit in systems with plasticity is not a simple thing. I mean,
Well, I agree, but I think a sample with 1,000 Lennard-Jones particles might as well be marginally stable.
It doesn't look like. I mean, thousands. It's not big for many MD simulators, but it's big enough to do some. No, I mean, at the practical level, there's definitely a scale where you will run into, precision problems and so on and so forth. But it looks like from what we are here, we are far from it. But it's something that you have to think about ultimately. Okay, that's for sure. So I'm going to sweep this under the rug.
Yeah, I was just thinking about I guess you've mapped out this graph well below the irreversibility transition. Well,
No. I mean, it's actually, no.
Are there sinks, I guess, within the graph?
No, you see, every deformation, every path here is a deformation path. And so if I start from here and I just basically go along the gray arrows, somewhere out here is yielding. Okay, it's on this graph. I mean, it's on this graph, and it shows itself in a change of local topology.
Interesting. In what sense does it?
It becomes more tree-like, for example. You can actually quantify this. As you're starting to approach yielding, and you're starting to proliferate new states. It's the degeneracy of where different paths are coming back to the state is basically lost, gradually lost as you approach rigid. Which means around yielding, you're really having a genuine sort of binary tree that is starting to branch out. Every instability leads to somewhere new. Yes.
So you say that this tree depends on your initial condition, your initial random state. But if I now would start at another random state and build this tree, is it possible that these two trees connect at some point? If they connect, are they then?
Well, look, I mean, this is where I started, right? So I could just take any point here, right? Which I get from this by doing some weird deformation, right? And then I can grow it from here. These are all part of the same tree.
So this means that if you just run like this tree building program for, let's say, 1,000 different initial conditions, and you glue all these trees together, then you get some sort of a total description of your whole.
So yes, I mean, so we are talking, yes, and yeah, we're basically hoping. I mean, I'm hoping that if I do this with 1,000 different prepared samples, okay, there's certain statistical properties that basically will be common across them, so that it really makes sense to talk about an ensemble. I could take this configuration and then I could just mess up the coordinates of a few particles here, right? And then start to grow a tree from here and see when do they start to diverge? When do they start to converge? These are all games that you can run on this. But I would again say, if you just barely look at particle configurations, you're not seeing the forest because of all the trees, okay? It's this kind of, basically looking just at the plasticity and the instabilities basically allows you to put your focus on something where you can actually compare things. I mean, I can also, I can take this and then I can take maybe a spin glass, okay, which is a completely different system, and I can generate, these graphs for that, and I can ask, how different is the topology from the spin glass model that I get, versus this atomistic, this sort of thing. In the end, they're all coming down onto the same graph structure. So I can ask, I can compare, if you like, apples with oranges, because, ultimately it's, you see what I mean? Because it's, in the end, it's, how does it, defining the right observables, right? You can basically compare these things.
I mean that you would expect that the topology of the graphs are different from one system to another.
I don't know, but at least I have a common ground. I can take the spin glass and get a glass, on the magnetic field, right? Instead of shear, and I get a graph. And I take my amorphous solid under shear, and I take a graph, and now I can start. I mean, at least I know how to compare graphs. I don't know how to compare a spin configuration, with an atomistic configuration, but I know how to compare graphs. Okay. Yes.
How can I, okay, so how do you think about the bottlenecks in the graphs that you see? Like, do you have a physical understanding of what?
Yeah, so bear with me. Again, your task is to ask this question at the point that you think is sort of, I mean, but it's, I mean, I'm not going to give you answer, maybe the purpose of this talk is there's a lot of interesting questions that you can ask once you look at the system in this way, okay? And I would really encourage you, go out and explore and, tell me. Some of these questions I will answer, some of them I will answer in a way that may say, but, this is not the whole story. So dig deeper, okay? But the thing is that there's, this is a handle on something that initially looked kind of quite, unmanageable, okay? So this is the, okay, so, yeah, so I think I have said everything that I wanted to say. Now, okay, as I said, where did we start from? We started from cyclic or random deformation, right? Every deformation protocol is a path on this graph that leads somewhere depending on the kind of deformations that you've chosen. So, where is my response under cyclic shearing? Okay. So I start here and I apply a cyclic shear at a very low amplitude. So first the strain increases, so I follow the black arrows, then it decreases, I follow the red arrows, it increases, I come here, then the red, and limit cycle. I start here, now I make the strain amplitude a little bit larger, okay? So I go up to here, now I decrease the strain, I land here, I increase the strain, I land here, I decrease it, I land here, limit cycle, very quickly, okay? Now I make it even a little more bigger, then I land here and here. Okay, so these are a bunch of limit cycles that are reached very quickly because the amplitude was not very, very large. So now let's look at this limit cycle. So the x is the state that you reach when the strain takes its lowest value. The y is the state that you reach when it takes its largest value. And this is what you get. Sort of as you're starting at the bottom, you increase the strain, you go through a bunch of transitions until you reach y, and then you go back through these transitions until you reach x. So this is my train state. If you drive it at that amplitude, it exactly retraces itself. Now you say, okay, what would the readout be? Well, you would start from your train state, and instead of going all the way up to here, you go maybe all the way only up to here, and then you turn around. So I need to sort of ask, what happens to the other instabilities out of the state? Remember, every state has two instabilities, right? So then I can fill this, and this is what I get. And I have placed the vertices in order to show you that there's some structure. So there's some structure, you see, if I go up and then I come down, I return to here, I go up and come down, I return to here, and then I can go up here again. So you see, I see, I got more than I asked for. What I asked was, I drive it cyclically, I want to get the cyclic response, that's that. You go up, the black arrows, you come down the red arrows, and then you go up again, and it's the same. But, the system gave me more. It gave me a hierarchy of nested cycles nested within each other. Again, this is emergent. I mean, this was not in the system. Okay, whatever I did, by this training, by altering its microstructure, yes, I got periodic response, but I got a little bit more than that. Okay, so so here I'm showing you this nest. You see this cycle is a subcycle of this one, and it has a subcycle this one, then it has a smaller cycle. It's, if you are familiar with magnets, this is the nesting of hysteresis cycle. This is something that is associated with what's called return point memory. And this is sort of, this is not a magnet, but it's kind of, in some sense, it mimics a magnet. And now we kind of can also understand maybe what's happening with this readout. So I trained it, and I not only got the cycle, but I got this sort of local set of cycles and subcycles within each other, which means that if I now do a readout at an amplitude that is not so large, so that I don't exit the cycle, right? I'm here, then I might be returning. You know, I stay within the cycle, you know, before I get out. The exits out of there are from the extremes. And then there's here one bizarre one that I will talk later about. But you see, this is kind of like an island of reversibility. So, you know, one of your questions, this is a directed graph. What does the topology tell me about it? Now, what I claim is pick any two states, say this and this, okay? For any two states, there's a deformation path that goes from this to this, and there's a deformation path that goes from this to this. How? Okay, so how do I get from here to here? I go down, I come here, and then I come down here. I'm there. How do I get from here to here? I have to go up, and then I have to come down, and then I have to go up, and then there. Any pair of states is mutually reachable. There's a path, directed path from A to B and from B to A. Mutual reachability is an equivalence relation. So you can basically partition the set of vertices on this graph with respect to this equivalence relation. It's a partition, so every state can only be in one equivalence class. These are called, in graph language, it's called strongly connected components. Any periodic behavior has to be confined to a single strongly connected component by definition. Okay, so the statistics of these strongly connected components, their sizes, their dynamical accessibility, basically spells out your hopes of whether you can land in some limit cycles at a certain size or not. I mean, the larger the amplitude, the more plastic events, so the bigger the strongly connected components have to be that will track them. Okay, so these will be the attractors of your dynamics. Okay, that will track them. So this is one handle on these things. Okay, so hierarchy of nested cycles. So yeah, so we've talked about the strongly connected components. And this is a generic phenomenon. So we have Dor here, Dor with as part of the Laini group, you know, this nesting of cycles. You take a, well, he's the man. You take a wrinkled sheet, you load it under compression. It's a thin Mylar sheet, and you get the stress-strain response, which shows this nice nested hysteresis cycle in the form of memory that I've been talking about. So, in fact, I liked it so much I was allowed to write a commentary on this. Yeah, so I'm kind of really biased on this. But now, okay, so this is all, if you like, phenomenology, right? I mean, I've taken this and I've mapped it into a graph, but what's the physics behind this? See how we're doing. Okay, so what's the physics behind this? Well, as I told you, as we discussed, you know, during each of these transitions, there are some localized instabilities in the sample. So now we are going from the abstract graph description back into the configuration of the particles. And, you know, as I share it, at first things are moving continuously until a localized instability starts out, a rearrangement which moves particles around. So, you know, with this outer loop here, you know, every transition means somewhere in the sample, there's some rearrangement. So what I've done is I've plotted, this is the sample, I've plotted the locations. You know, here there's a rearrangement 1, this region rearranges. Then from going from here to here, region 2A, these two regions rearrange. And then, you know, the regions 3 rearrange, and so on and so forth. So as I go from here to here, these green regions undergo rearrangements. And then when I come back, they undo the rearrangement so that you're returning again to the same state. Okay? And what's interesting is what happens in a subcycle, if you enter into a subcycle, you're basically only a subset of these states rearrange. Okay, so you have kind of like mechanical bits that have come up that turn on and off, okay, as you reverse the cycle. And a subset of them turns on and off when you go into a subcycle. So these turn out to be, again, these turn out to be, they have two state systems, a state that I will call 0 and a state 1, because it's kind of binary. And they switch hysteretically between the 0 state and the 1 state. And you see, this means a local plastic event where some particles rush out and others move in. And then the reverse of it is now the ones that move in rush out, and the ones that moved out now rush in. Okay, so you switch hysteretically. But you see, whenever something like this happens, it messes up everyone. This is the important thing. These soft spots, when they change, they alter other soft spots, you know, instabilities, localized instabilities, which are called soft spots. They alter the switching behavior of other soft spots. they can do more. They can create new soft spots. Okay. But they can create new instabilities, or they can disable existing instabilities, meaning that when it's disabled, it responds elastically. Okay. So you have sort of a gas of soft spots whose number is not conserved, that is interacting with each other, that as a result of the driving, you're creating new soft spots, you're destroying someone, but whatever creates depends on what soft spots you have available at that point. And this training basically now is basically finding a set of soft spots that are localized in such a way that they can switch without messing each other's behavior. This is what I call a persistent set of soft spots. Okay?
They become uncorrelated when you say they don't change each other.
They are correlated, but not so much that it basically. Okay, so what could happen? You see, it's this one. When you see everything was fine. If I go halfway and come here, I'm just if I'm unhappy and I'm coming down here, I'm suddenly creating a new soft spot that was not part of what I had trained for. Okay, and that new soft spot basically means that it basically throws a wrench into the system, and once I trigger it, the system evolves into a completely different part. That creates so the training is trying to get you a bunch of instabilities that are basically preserved, okay, but I mean, it's not guaranteed because, as I said, I mean, I was asking to get a periodic response. I got a hierarchy, which means the soft spots that were responsible for the periodic response were kind of mostly playing nicely with each other. But because of the frustration in the system, okay, I mean, there can be some sort of, there can be some twists, okay? This is where the system is different from what would be a ferromagnetic or so. This is the fact that you're stabilizing and destabilizing at the same time allows these things to happen. But this also allows the system to sort of evolve. This is also why we were thinking of maybe if we do a random driving protocol, then the ultimate attractor would not have these things anymore, these premature exits, because if something is stable under random driving, right, it's in some sense it's stable under any possible protocol that remains out there, right? So you're shaking out these premature exits. Okay, so maybe with that I will skip. These graphs, these interacting instabilities can give rise to quite some complex behavior. You can interpret these graphs as a finite state machine. Your colleagues in Amhoff, Martin van Hecke and his group, I mean, they have basically explored, the designer path, what you take with designing these instabilities. But I want to sort of just hone in a little bit more on this emergence of these soft spots. So let's revisit this issue of training again. I mean, the training, I'm cycling this system, right? So I'm creating soft spots, and these created soft spots create new ones, destroy existing ones, and this continues until I reach a system of persistent soft spots that basically can be repeatedly triggered. And with that, I basically get, I get this sort of structure of this mechanical reversibility. I think it's at the soft spot level, being able to attain a system of persistent, soft spots that interact with each other, but mildly, so that they don't basically disable each other, okay, which has to do with their spatial patterns, okay, the further they are away from each other, the less they affect each other, okay, is basically a stable attractor for the system, okay, and that is the process of self-organization. So your driving conditions basically put now I'm going to use it in this way, a selection pressure on these soft spots and favor a certain set of soft spots that can survive this driving condition, and thereby give rise to a steady state. Okay, and so this is the memory basically, in that it's encoded into the microstructure, namely into the set of emergent soft spots that under the conditions that you have imposed, be it cyclic shearing or random driving, okay, under those conditions, these basically survive. Okay, and this has I'm giving it a deliberately biological twist, because this is a mechanism of adaptation. And this is a mechanism, I mean, this is sort of the physicist's, maybe poor man's view, it's an evolutionary process, if you look at it at the formation of soft spots and so on and so forth. So I think maybe at this point, Generalizing this to random driving, well, you may not get this nice hierarchical structure, but you may instead get these strongly connected components where, again, stuff remains highly reversible unless you exceed the boundaries of the driving. Again, it's a region in this graph that is with high reversibility, whose fingerprint is a set of soft spots, that basically emerged as a result of the driving. Okay, and so with that, maybe let me give you a summary of what we've done, and maybe this is sort of, well, let me give you a summary and I'll ask you a question. We started out with the shoes as sort of a system whose behavior adapts to its fluctuating environment, some random fluctuating environment. We go to something simpler, a two-dimensional system of particles interacting with binary Jones interactions and amorphous solid. The dynamics, as we said, was driven by the soft spots, localized instabilities that basically propagate stresses onto other parts of the system, thereby creating new soft spots, disabling them, altering the stretching behavior. A natural way to describe this is in terms of the transition graph, because we are under athermal quasi-static conditions. So this way, I've basically converted a system of continuous degrees of freedom into something that is discrete and amenable to theoretical analysis. The key object in these graphs are the strongly connected components, regions of mechanical reversibility that are basically spanned, if you like, by the soft spots that are active in that strongly connected component. And so these are maybe the key insights and ingredients that we should get from this Gedanken experiment, if you like. The system that we started out has many degrees of freedom and disorder, and this gives rise to this deformation landscape, which we are probing by this graph. The mechanical deformation, so it can be in many states. The mechanical deformation that I apply is a process of state selection. The system basically, selects a state as a result of applying certain deformations, and a certain kind of deformation selects maybe this kind of states, other deformations select other states, and it's this correlation between what you apply and what you get, which ultimately encodes the memory. Okay, if that correlation was not there would be no memory. Okay, and this is all, this reversibility in some sense, a key ingredient, but not, it's necessary, but probably not sufficient, is that although the system is high dimensional in its configuration space, the driving is low dimensional. So effectively, most of the coordinates of the particles are slaved to a few dimensions. Okay, so this is a slow manifold on which things are evolving. And this is why this problem of getting reversibility is not like searching a needle in the haystack. Okay, effectively, the system is much lower in dimensions, because of the imposed conditions of athermal quasi-static things. And this is why you may have a chance of getting reversible behavior. And so it's basically instability. So the dynamics at the level of plastic events is discrete. And that discreteness is basically what is captured by the transition graph. So, do we have time for another 5 minutes? Then I would sort of take a deep breath, and then I would ask this question. And this is now from here onwards, we are getting into the speculative brainstorming part, okay? And so the question is, what can this story that I've told you tell us about how simple organisms that lack a brain, meaning that they don't have a nervous system, information processing capabilities as we know and associate with ourselves, what can it tell us how such organisms adapt to their changing environments? Okay. So I'm going to revisit what I've seen, from a biological, buyer's perspective. I'm a biologist, how could I buy this, or how can I sell this to biologists? But this is sort of, I think there is something to this. This is why I'm standing behind it. This is not a matter of, this is a matter that I think this is something that may have been overlooked and it's worth looking at. Okay, so let's look at this self-organization under some deformation, be it random or cyclic, leads to a set of persistent instabilities, which means I basically have transitions here that basically, can be repeatedly triggering as long as I don't change the conditions of the driving. Okay? Which means that as I sort of, as the system is doing some weird fluctuations here, inside here, I'm going through some transitions here, okay? Which means if I just observe the transitions in the system, I can infer something about what's going on outside. Because you see, this sort of, this deformation protocol leading the system into a steady state has established a correlation between the state changes of the system and the dynamics of the environment. And it has actually done a little bit more because this is not only measuring the state, there are many states that are maybe stable at say, at this value of the strain. However, you see, I'm capturing part of the history dependence. If I end up in this state and I land in this state and they're both, say, at the same strain, I know that the only way I could have gone through this is that if the strain had first gone up to here and then had come down here. There's no other way that I can go from here to here. Okay, so it's not, although these are basically at the same state value of the environment, okay, in order to get from here to here, something must have happened in between, because otherwise I wouldn't be able to get there. So this is basically also a system that not only measures the states of its environment, but it also filters out some historical information. Not perfectly, but there's information that this thing so it's mapping environmental histories into internal state transitions, histories. Okay, so, this is what we said. We will keep this. So in some sense, this is a pattern recognition problem that you've solved. You're basically recognizing environmentally changing history patterns, are mapped into kind of, state transitions, within a, more idealized and combined. This is sort of, in some sense, if you want to think of it, this system is doing some form of pattern recognition, as we know from, this is sort of a classic machine learning problem. You want to recognize written digits, handwritten digits. You want to map them into some internal representation. Okay, there have been people that have been sort of, hypothesizing that sort of mapping your environment into some internal representation is important in order to do any kind of prediction. Bayesian inference, is basically a way of representing the data or your environment in some complex or condensed, representation, and using that information as input to making predictions or estimates. So you see, this is something in this system, or in the system of a crumpled thin Mylar sheet, you get this infrastructure for free. Okay, it's there. Okay, you get this infrastructure for free, and the question is, does nature exploit it? It's out there, and someone once told me that, and I found this very, nature has a criminal mind. Nature exploits loopholes. Okay, this is what evolution is about. You want to get an advantage. So you basically exploit what is possible to the furthest extent to get some kind of advantage against your competitors. Okay, so is this has nature discovered these features and used them to their advantage? And here's maybe from a paper, the title which I like, which sort of summarizes this slogan: self-organization proposes what natural selection disposes. So you get this infrastructure, and ultimately it's up to nature to decide whether it can do something useful or not. But here's the proposal. Does selection really run on this? So maybe this is probably a good point. So maybe let me just stop here. This is if you want to read more, a lot of this is sort of expounded further in this annual review that I've written jointly with Eric Clement, Damien van der Broek, and Shrikant Strastri. And a lot of this, the names highlighted here in bold are sort of who have directly contributed to what I've just basically told you. But this is part of an ecosystem of collaborators within which these ideas have been bounced. And with that, I want to thank you. And this was research funded by the German Science Foundation. Yes, so thank you very much.
I think for the talk, we get a call for an hour about these things. So talking about the last few slides, So in the first part of your talk, it's really one of the essential assumptions is the rate, there is no rate dependence.
Mhm.
Whereas in biological systems, there really is a rate dependence, like a bacteria searching for, food source or whatever, following a sugar trail. They're really the rate of change in how the signal enters the bacteria really is important. So in what sense does your story of the first part translate on the second part if you account for this rate dependence?
I think this picture will not break down the moment you add rate dependence or temperature. I mean, it's not going to be like a singular perturbation, where the moment you add even the smallest amount of perpendicular rate, this picture will evaporate. There is a limit within which probably some of this will be more or less true, but not exactly true. I mean, it will be like kind of the temperature will smear out this, I will not maybe microscopically return exactly to the same configuration, but I will remain within a cloud of the same configuration. Then I would assume, and I mean, there's sort of, there will certain things be that are basically not captured by the rate dependence. But, maybe within a certain regime of operation, it may not be so important. I think though, and again, maybe let me stress, I mean, in my mind, I think there's interesting physics here, even in the limit of, but I think there's also, and this goes actually back to sort of, there's also, this is a setting where you are basically able, it's maybe an idealized setting, and we may not capture reality, in the fullest extent that we want. But I think it prompts us to ask questions, okay? And that, whose validity or whose consequence may go beyond, it prompts us to look at the system from a new point of view, okay, which might help us when we stare at systems where even rate dependence or temperature is important. I think, the real value of it is basically, I took an idealized system, but, what I have done is essentially has been rigorous in the terms of, it has a natural description of a graph, the topology I brought in, I mean, I've hand waved, but not, it's at the level that the theorists would be reasonably confident. And it has basically, it has brought up a picture, okay? This picture, I think, may have a validity, I would hope, that goes beyond just, rate-independent athermal systems. I mean, it's in that sense, it's metaphoric. And this claim of metaphoric goes actually back to it's not my invention, it's Jean-Pierre Bouchot. These are systems that basically that point you towards mechanisms like something like this may be used by biology. Maybe not in a system where rate dependence is important, but there are, it's the realm of biology. Adaptive evolution is sufficiently broad that there could be niches, where these mechanisms are relevant. Yes.
I have a couple of questions.
Sure.
One is related to this, because in mechanical systems, when you add the temperature, for example, then you observe a creep, which might destroy these loops, let's say. So in other systems that are not necessarily mechanical, so by biology or something like this, would you expect something like creeping? You have time scales involved, so some aging dynamic.
Yeah, I mean, absolutely, yes. I mean, this is basically that will come in. But again, this picture could, I mean, yes, in the reality, there's also creep. If you wait sufficiently long, even if the barriers that separate you are very high, they might eventually be overcome. I mean, then all of this is basically taken out of the picture.
And also, my second question is that you spoke about soft spots, right?
Yeah.
And there are in disorder systems, you can have like soft spots, so this localized excitation, but depending on the system you have, you can have also system-wide excitation that, for example, you cited the spin glasses, there you don't have necessarily soft spots, but when some spin rotates, you have this avalanche that involves the whole system. So don't you expect that in that case, does the same picture applies in those kind of systems, or is it different? Then, would you expect still this reversible plasticity, or then you end up just in a full plasticity there?
No, I mean, you know, it's the I mean, for one thing, you know, the closer you get the system towards yielding, okay, I mean, you're basically increasing the concentration of soft spots, I mean, the density of soft spots, and which means effectively you're increasing the interactions. So in that sense, you see, I mean, I said the system is low dimensional as long as everything is responding elastically, right? But once you get to the instability, the system is intrinsically high dimensional. You know, there is a relaxation pathway that will basically explore part of this high dimensional configuration space. And this high, you know, until it finds a new basically configuration, which again sits on a one-dimensional manifold. Okay. And as you get closer to yielding, you know, that transition, you know, that I've kind of said, look, it goes somewhere, I don't care about where it goes and how it does, it's just a transition in my graph. That transition, of course, will start to matter. And it, you know, but again, this is exactly where you get into in the graph, you know, this is where you get into tree-like regions, you know, where the strongly connected components become extremely small, meaning that, you know, wherever you get, there's almost no chance that you will return to it because, you know, effectively, you know, it's maybe a system spanning avalanche, you know, you've messed up too many particles, okay, along the way.
Yeah, exactly. This was my question.
Yeah.
So in these kind of systems where you have not necessarily soft spots, but system-wide excitation, do you expect to directly end up, do you still expect to find these
No.
loops or?
No, I don't, no. And you will see this in the topology, you know, I mean, you see, this is a random graph, but it's not a homogeneous random graph, okay? I mean, that's the key point. It's not a homogeneous where every point of where the neighborhood from any point looks the same. That's the whole idea. This graph is an evolution process. And, you know, its properties, its local topology changes, okay? And that's what you would like to capture. And so, you know, around yielding, its topology will be different from what it is where you started out with.
But is it a function of a strain was right?
No, it's maybe let me go back to this because this is important. I mean, you should think of this. You see, this is kind of like, I mean, look, this is my initial glass before training. Every possible thing that I could do to this glass, okay, as long as I'm athermal, rate independent, every possible thing that I can do to this glass lands into a state that is somewhere on this graph. Maybe not on this part here, but you know, it is, you know, it's you know, every possible deformation protocol that I do to this one common glass is a path on this graph. So this is kind of like the phase space of classical dynamics. You know, I'm not looking at individual trajectories, but you see, it basically, it's the flow of glasses, you know, under the space of different deformations. Okay, so it's kind of like the phase space description, you know, rather than sort of equations of motion. Okay, and that's how you should think about it. So, you know, the regime, what Tommaso was saying, where sort of, you know, you have a huge, you know, system spanning soft spots, you know, events, you know, are on this graph. And, you know, and they must be basically make themselves visible by a change of local topology of the graph. But in principle, you know, this graph contains everything that you could possibly do to that particular glass called O, okay? As long as you're just shearing along a fixed plane on the athermal groups, okay? I mean, yeah. So that's why you would like to understand its structure. It's its phase space, if you like, on the deformations.
I was intrigued by sort of the analogy the question you phrased in the end. It was one of the questions I wanted to ask you, but it's not completely clear to me, like, what is like, how concrete is the analogy? Like, if you move to living matter, do you really consider like physical strains on living matter, or should I think about it way more abstractly, like evolutionary pressure or something, or the pressure that the environment exerts on the actual evolution of organisms, and so what's the degree of
how serious should I take this picture?
How should I think about this picture and the graph you showed in the biological?
Okay, so I think maybe let me start with, I think one sort of I mean, as I said, I'm just going to sort of, I think these are these are exactly the questions that one should ask. And, when you ask these questions, you need kind of like a reference system, something to measure up against or so. And I think, in my mind, this is sort of maybe the way of, this is kind of your base thing. And, we've seen this in a realm where we understand it. Can we apply it to somewhere else? One of the things is where I would like to sort of see this is, you have a system with many degrees of freedom. I think part of this mechanism is generic. Okay, you have a system with many degrees of freedom, and you're driving it at in a low-dimensional way. In my case, it was the most extreme one-dimensional parameter. But you have some form of slow manifold. Where a lot of the many degrees of freedom of the system are slave to a slow manifold, and then you can basically move on this manifold until you get into some instabilities. And these instabilities, do cause you to a rapid change from one slow manifold to another manifold. And I think this sort of reversibility and so on is maybe to a certain extent generic. I mean, as long as you have sort of these transitions fall into a certain class, it's, these vertices are essentially the slow manifolds, okay? And the transitions are between slow manifolds. You may ask, does something similar like this happen in a chemical reaction network? Where your configuration degrees of freedom are now the species, the concentrations of the species, and you have chemical reactions, that may deplete some species, create new ones. You have autocatalysts and so on and so forth. And then maybe you're driving the system by cranking up the oxygen level or the ATP level, ADP level, or something like that. Okay, it doesn't have to be an amorphous solid. It is maybe a system with sufficiently large degrees of freedom and a slow manifold on which you can drive with a few controls, like a chemical reaction network. So we have, might sort of show things like this and history-dependent behavior. So then you could ask, rather than shearing, I'm cranking up and down the oxygen concentration, or what people have done with bacteria. I'm just basically switching between lactose and glucose, and the metabolism of the bacteria has to adapt to this. And so, you could sort of, and I think this is what people should be doing. It's at a certain level of abstraction, and clearly the devil is in the details, but at a certain level of abstraction, it's a system of many degrees of freedom driven at low dimensional, are there similarities? So that's the one part. It doesn't have to be an amorphous solid. The other thing is, if you think about adaptive evolution, then it's a lot of these ideas have gone back and forth between statistical mechanics of disordered systems and sort of, what is called in biology, it's called the fitness landscape, which goes back to Kaufman and other people, okay, which again is, you have a landscape. In the physics case, you have an energy landscape. In biology, they have this thing that they love, the fitness, which is sort of a growth rate. And the idea the mantra in biology is evolution tries to increase fitness, and fitness, of course, depends on genotypes and so on and so forth. But people have described these in terms of a fitness landscape where, your configurations are the genotypes maybe, and, you ascribe to each genotype a fitness, and there's an evolution towards higher fitness. And then, these fitness landscapes can change because they may depend on a control parameter, like the concentration of glucose. If you increase it, then certain genotypes may be less fit, become less fit. In fact, with my collaborators in Cologne, so there is definitely, even on an adaptive level, this parallels between evolution on an rugged energy landscape with lots of minima, or a rugged fitness landscape. There's been lots of crosstalk between it, and it's also work that I've been involved. And then this is sort of like a fitness landscape that's changing in time because you're changing maybe the concentration of nutrients, or you're changing the concentration of a drug, an antibiotic, which makes certain genotypes more resistant and gives them an advantage, and others less resistant.
Just a quick comment related to our question. So if you look at the graph that you showed, this is known in the review by Susanna Manrubia or Michael Lassix. This is a so-called the neutral space. So each node in the graph is one genotype. Yeah. And you move along this tree network structure without changing the fitness. Yeah. This is the so-called neutral space. Yeah. And this is one concrete example of biological application of that framework. Thank you. Yeah.
So you know, I'm not going to claim that this solves all the problems of science or something, but I mean, but you know, far from that. But you know, I think this is at least a point of, you know, I think in order to understand something, you need to start with some biases, and you know, some plans or some ideas, and then you know, the interesting thing is, of course, when you figure out that nature does something completely different, you know, and surprises you, you know, and it's not what you thought it was. Okay, but I think you have to start somewhere, and this is sort of the way I would like to look at these systems, and you know, and you know, what would be the counterpart? You know, it's what do I need? You know, how generic is this mechanism?
Next question.
If there's time.
Yeah, maybe, and then we have.
I will bring you back to my old question, but like basically, so going back to the graph.
Okay, shall I bring the graph up?
Yes.
The full thing, right? I mean, you know, the kind of. Okay, so. Yeah, this one.
So there are, like if I squint enough, there are 3 topological regions where you have these loop-like structures,
Yeah.
bottlenecks, and these branching
Yeah.
regions, right? And if I'm not wrong, if you go past the yield stress regime, you are in the branching,
Yeah.
that kind of regime. So these bottlenecks are like kind of generic because they are taking you from this loop-like
Yeah.
these branching.
Anyway, yeah. And you know, maybe this is, you can also kind of see this here quite clearly. You see, I mean, you know, from any of these states, you know, if I increase the strain, you see, they all go first to the state Y before they exit. You see, oh, thank you. Okay, you know, what came out of the cyclic shearing was not only the hierarchical nesting, but if you ignore this premature kind of exit, okay, I mean, from any of these states, you know, you exited either from here or from here, okay? So, you know, because, you know, that's basically coming towards the extreme condition where the system can kind of barely hold up, okay, and then the cards need to be reshuffled. I mean, you know, new instabilities kick in basically, which basically sort of alter the system in such a way that apparently you cannot return to it. So this is this focusing that's happening.
But does that explain the presence of these bottlenecks in the graph? I can imagine more cyclic or like loop-like regions to just.
I mean,
expanding.
no, I mean, it's, I mean, you know, in some sense, this is a bottleneck. You know, if you want to go from here to here, you know, many states have to go fast to here, but there's probably more to this.
Yeah.
There's probably more to this.
Is there a sorry? Is there one purpose? Is there a way to order these states? So is there a mechanical parameter that can order these states hierarchically based on how they are nested with each other? So, for example, if I'm thinking about the soft spot, for example, the stiffness of the soft spot. So Y and X are the highest, for example, or some other parameter.
That's a good question. I mean, you see, that's a good question. I mean, you see, it's by plotting them the way I've done them, or plotted them, there's a certain, you know, there is a certain hierarchy that you see here, loops within loops. And, you know, with each of these loops, I can also assign the soft spots that are changing within the subloop. So in that sense, you know, the tree, you know, if this has this perfect hierarchy, which in general it will not have, okay, then there is a certain ordering that this loop structure gives you, you know, because you see, with every loop, you can identify the soft spots that are active in it. But the same soft spot can be active in many different loops, okay, and its activity will depend on the states of all the other soft spots. Okay, so it's not, I mean, there are ideal cases where you assume that the soft spots are not interacting at all, they are just there, okay, and then it becomes simpler, and that's what's called the Pryzak model. It's an elementary model of hysteresis that's almost 100 years old now, that also you can look up some things on, you know, but with the interactions, you know, it's the switching behavior of a single soft spot depends on its background. And again, you know, from a, you know, whether a certain mutation of a gene, again, you know, this would be something that biologists would tell you, oh, this is like epistasis. namely, a certain gene, whether when it's mutated, whether it becomes advantageous or not, may depend on the mutation states of the other genes. Okay, or in magnetism, whether a spin flip in a random field Ising model reduces energy or not, may depend on not only the single spin, but also, the configuration of the other spins. Because of the interactions again, the interactions may stabilize or destabilize, a certain transition. I think you have a question. Okay.
Thanks again.
Thank you very much.